Okay, so the first one you sent me was this one where you're looking at the two standard triangles. And if you haven't looked at how these triangles are derived, in section 5.2, I talk about these special triangles. So if you're looking at like where did these numbers come from, they're derived, and the review video for section 5.2 talks about how we do these numbers. The one that we're looking at in this case is going to be this one, and this is derived from actually an isosceles triangle, where we know an isosceles is where all sides are equal. So all sides with, if you have 1 over here, then 1 plus 1 is 2. It's an isosceles triangle. And then from that, we derive the rest of the features. So I'm not going to go into how we derive these triangles. You can see that on the review video for 5.2. And they gave you them so you don't have to derive them yourself. TJ, did you see the study sheet that I posted in the news feed, the trig study sheet that you can include in your, because it's a proctored test, you're allowed a study sheet. These triangles are included in that study sheet. Awesome. So if you use that as part of your first page, those two triangles are there. So what they're saying is use these triangles to express the value of tan of 30 degrees, and they don't want it expressed as a decimal. They want it expressed as a square root as possible. And the reason for that is that most of the times when you are expressing something as a decimal, you have to round off. So it's not the most precise answer. If you can give it as a fraction, that's much more precise because you don't have to round off. A fraction is a fraction. It doesn't need to be round off. So let's look at this tan of 30. They're saying express this tan of 30 degrees using the triangle. And the triangle that we're going to use is the second triangle. And the only reason why we're using this second triangle is that here's the 30 degrees right there. This first triangle with the 45 degrees and the 45 degrees and the 90 degrees, it doesn't even have a 30-degree angle. So we don't use that. That's used if we're talking about 45-degree angles. But we're not. We're talking about a 30-degree angle. So that's why we're using the second triangle. It's a special triangle that, that everybody needs to know about. It's also on that study sheet. So TJ, are you okay with that, of where we got these triangles from? They're just a standard triangle that we're using. Okay. So we're going to use this 30 degrees, which is right here, and we need to express the tan of 30 using this triangle. So the first thing we need to do is identify our sides. If our angle is 30 degrees, then we are going to be looking at exactly opposite of that is going to be our opposite side. Beside the 30 degrees is going to be our adjacent side, which makes this our hypotenuse side. So I'm just identifying the sides, opposite, adjacent, and hypotenuse. And we know that whenever we do tan, tan is going to be TOA, which means that's that acronym, right? Like SOHCAHTOA TOA helps you remember what the ratios are for each of those trig functions. So tan is TOA, which means opposite over adjacent. Are you okay up to that part, TJ? Awesome. So once you know that the ratio for tan is the opposite over the adjacent, we can then use this standardized triangle, and we can look at what's our value for the opposite. It's 1. And what's our value for adjacent? It's the square root of 3. So the tan of 30 degrees is equal to 1 over the square root of 3. Now, this is in radians. So if you were looking at the tan of 30 degrees, that's the same as saying pi over 6. So the tan of pi over 6 is equal to 1 over the square root of 3. So if you were to put in pi divided by 6, and make sure your calculator is in radians, and then take the tan, that's going to give you the same decimal value as taking 1 divided by the square root of 3. The only problem with this is that in simplest forms, when you give a final answer, they don't like to have the denominator, that bottom value, as a radical or as a square root. So what they want you to do is to rationalize the denominator. So this is the last part of this. If you were to answer that the tan of 30 degrees is 1 over square root of 3, I would give you 0.75 out of 1 point. But you need to simplify it all the way or reduce it all the way in order to get the full mark. So when we do that, we have to rationalize the denominator. And when you rationalize the denominator, you're going to just multiply the numerator and the denominator by the square root of 3. That gives you the square root of 3 on top. And the square root of 3 times the square root of 3 just gives you 3. So the tan of 30 degrees is evaluated as the square root of 3 over 3. That's how you find that out. So that's the answer to this question using that standardized triangle. So you had to first figure out which triangle to use, and then from there identify your signs, like your sides, sorry, which is the opposite, which is the adjacent, which is the hypotenuse. You needed to know that your ratio for your tan is going to always be your opposite over your adjacent. Plug in your values, and then to get the final answer, you had to rationalize the denominator in order to get your final answer. TJ, did I lose you someplace in this? Great. Okay. So no questions about this. We can move on to your second question. Yep. Okay. So now I need to go and find that. Whiteboard number 2. Okay. So this is your second question. Here we go. Okay. So this one, it says find the exact value of expressions. Do not use a calculator. And in this case, we are going to use that trig study sheet that I gave you because our special angles are on that. And we also need to use some trig identities to also figure this out. So the first thing that I see when I see this is I need to simplify this, tan of pi over 3. And if you have your trig study sheet nearby, do you have that by any chance? Have you got that printout beside you? Okay, so if you look on that trig study sheet, I have all the special angles. I have 30 degrees, which is pi over 6, 45 degrees, which is pi over 4, and 60 degrees, which is pi over 3. So pi over 3 is 60 degrees, and so right away, you don't have to derive that. You know that the tan of pi over 3, or the tan of 60 degrees, is going to be simplified to square root of 3. And then because we have it over 2, I've just simplified that expression into the fraction of square root of 3 over 2. Are you okay with that, TJ? Okay, so you have to be able to identify that you're dealing with a special angle here, and you just take that tan of pi over 3, see that pi over 3 is a special angle, and it's given to you as the square root of 3. And then I'm just going to write down the rest of this, secant pi over 6. So 1 over the secant of pi over 6, this can be simplified as well. And what we know about secants is that they are the inverse of cosine. So we have the inverses of sine, cosine, and tan, which is going to be cosecant, secant, and cotangent. And secant is the inverse of cosine. So if I wanted to, I can rewrite this as 1 over cosine of pi over 6, because secant of pi over 6 is equal to the reciprocal of cosine of pi over 6. So 1 divided by 1 over cos pi over 6. TJ, are you okay with that? That's an identity that cosine is equal to 1 over the secant, and secant is equal to 1 over cosine. That's one of the identities that we have identified, and that's in section 5.2, where we talk about identities. Okay, so how do we figure this out? Yep, rewatch that clip. So there's a whole bunch of identities, and one of them is that cosine is equal to 1 over secant, and secant is equal to 1 over cosine. So all I've done is I've simplified this, changed it to a cosine, which is right here. And what that shows me is that I need to simplify this because I have, it's quite a complex fraction, right? I have 1 over cosecant. So to simplify this, I'm going to take the numerator and I'm going to divide it by 1 over cos of pi over 6. And whenever I'm dividing by a fraction, that's the same as multiplying by its reciprocal, cos pi over 6 over 1. So that means I actually have cos of pi over 6. That's what 1 over secant of pi over 6 is equal to. It's actually equal to cos of pi over 6. And you might be going, well, how did that help us? We're just going from 1 over secant pi over 6 to cos pi over 6, but I'll show you how that helps us. So we have the square root of 3 over 2, and we got that by simplifying the special angle of tan pi over 3. And we're subtracting now cos of pi over 6, because we found out that 1 over secant pi over 6 is equal to cos pi over 6. Teacher, are you okay with this simplified expression and how I got to that point? I can go back if you need me to. Yeah, it's also just looking at those reciprocal identities. That's where this cos of pi over 6 comes from, is that reciprocal identity. And as I said, how does this cos of pi over 6 actually make this 1 over secant pi over 6 more simplified? Well, back to the study sheet, TJ, if you look at that trigonometry study sheet, you see that sine, cosine, and tan are figured out for you as your special angles. So cos of pi over 6 is the same as the cos of 30 degrees. And if you look on that table, cos of pi over 6 is going to give you square root of 3 over 2. So we've gone and simplified even further. And now we have the square root of 3 over 2 minus the square root of 3 over 2 is going to give you 0. So this expression can be simplified to be equal to 0, which is a much less complicated solution to this tan over pi over 3 over 2 minus 1 over secant pi over 6. It's just equal to 0. So this is a proof that we're doing. We're just looking at simplifying this and finding a solution, and it actually works out very, very nicely. And that's what's satisfying about using these trig identities. You can simplify what's very, very complex into a very, very simplistic answer of zeros, ones by doing this type of work. And that is in section 5.2, is all about using identities and special angles to simplify expressions. So if you want to look over that review video for 5.2, that's where you're going to find this type of work being done there, your special angles, your standard triangles that we talk about, and these different identities. TJ, how does this sound? Are you okay getting down to seeing how you work out this type of a question? You're going to make sure you use your identities and you're looking for more simplistic answers for sure. And again, as I say always, on your test, if you get halfway through and you don't get the answer, but I can see that you're working through it, I'll give you extra points for sure. The identities, I think, are the hardest ones to get your head around. They take practice. It's almost like algebra for sure. Okay, and then the last one. What was the last question? Whiteboard 3. This is identities as well. So they give you, the nice thing about identities is that if you have sine, cosine, and tan ratios, from those ratios of your sine, cosine, and tan, you can then find out your cosecant, secant, and cotangent. And again, there's identities that use the sine and cosine, if given, to then derive your cosecant, secant, cotangent, and even your tangent. So these are your given values. Your sine of theta is 7 over 25, and your sine of cosine is 24 over 25. So again, I guess that the identities, I'm just looking back at the trig study sheet. Your identities aren't shown on your trig study sheet. So this would be something that I would add to the back of your study sheet are your identities, which are in 5.2. And I review them in the review video. You have your reciprocal identities, you have your quotient identities, you have your Pythagorean identity. You'll want to write those down because you're going to use them for this. So it's not on that study sheet, but you have lots of room to put them. So we are starting off with sine of theta is equal to 7 over 25. So our opposite is 7 and our adjacent is 25. And then we have the cosine of theta is 24 over 25. So in that case, our adjacent is 24 and our hypotenuse is 25. But what they want us to do is using identities, say what tangent is, say what cosecant is, say what secant is, and what cotangent is. So I'm going to use the identities. So if you don't have the identities written down somewheres, you can look at it in the textbook or look at the review video, and I give you all the identities, and I'm also going to give you the ones that I use for here. Does that sound okay, TJ? Okay, so let's do tan first. So if I look at my identities, I'm going to bring up the, just look at my notes here. There are two identities for tan. Tan of theta can be expressed as 1 over cotangent theta. That's one identity. That's called the reciprocal identity because tan of theta is the reciprocal of the cotangent for theta. But also, tan of theta can be expressed as a quotient identity. So we have reciprocal identity and quotient identity. And the quotient is going to be sine of theta divided by cosine of theta. So I have two identities that can help me out. Looking at the data that's given, which identity would you use? Would you use the reciprocal identity or would you use the quotient identity? TJ, which would you use, number 1 or number 2? Yes, exactly, because number 2, the quotient identity, has the data that's given. Sine's given and cosine is given. If you were using identity 1, you need cotangent of theta, which isn't given. So you can't use this one. Ah, that didn't work. Can I get that back? Undo. Yep. Nope. Yeah, okay. So you can't use that one. So what we're going to do is tan of theta is equal to sine of theta over cos of theta. I'm going to get a really complicated fraction at first. So sine of theta we have as 7 over 25. divided by the cos of theta, which is 24 over 25. TJ, are you okay with the data that I'm showing here? Okay. This is a complicated fraction. How do you make this less complicated? I'm going to take 7 over 25, my fraction. This line here, which is my quotient, means I'm dividing by 24 over 25. Are you okay with that? Just a different way to rewrite this. Great. And whenever you're dividing by a fraction, it's the same as multiplying by the reciprocal. So I'm going to get 7 over 25. I'm going to multiply by 25 over 24. That makes life a lot easier. I can just go 7 times 25 and get my numerator, and 25 times 24 and get my denominator, or I can see that I can cancel out my numerator and the denominator, and I can go right to the reduced fraction of 7 over 24, and that is what tan of theta is equal to. That's kind of nice, eh? That's how you use the quotient identity to derive what tan is from the given data. That's the answer for tan of theta. Is that okay, TJ? Great. Okay. So we've got tan. Now we need to do secant, cosecant, secant, and cotangent. And as always, I'd like to be able to move down in here, but I don't know if it will let me move down. Ah, good, it does. Okay, so my next one up, I'm going to do cosecant. So I need to find out what cosecant theta is using the data that was given. So cosecant theta, I'm going to use my reciprocal identity, and that is that cosecant of theta is equal to 1 over sine of theta. And I know that sine of theta is equal to 7 over 25, so it's going to be 1 divided by the fraction 7 over 25. It's a complicated fraction, but I know that that's the same as dividing by 7 over 25, which is the same as multiplying by 25 over 7. So cosecant of theta is equal to 25 over 7. And that's it for cosecant. If I could reduce this down into a smaller fraction, I would, but actually I can't. I can make a mixed fraction out of this, but they would just rather keep your answer as 25 over 7. TJ, okay with cosecant? 2 more to go. Okay, so now I'm at secant theta is my next one that I need to figure out. Secant theta, there's a reciprocal identity, and secants are always going to be the reciprocal to cos theta. And cos theta is given data, it's 24 over 25, so 1 over 24 over 25. That's the same as multiplying by 25 over 24. And so secant theta is going to be 25 over 24. And that's the answer to that one. And then the last one is going to be my cotangent. And that's, I've got 2 identities I can use for that. I can use the reciprocal identity of 1 over tan of theta, or I can use the quotient identity. And the quotient identity for cotangent theta is cosine theta over sine theta. And the question is, which one would I use? This is a complicated question. So TJ, don't feel pressure, but would you use identity 1, the reciprocal, or identity 2? Both will give you an answer. But there is a better one. Yeah, that is what people, it looks easier to flip the tan. And because we figured out tan here, we would just do this. But it's not the best choice because we had to figure out tan for ourselves. If we messed up on this and used it to figure out cotan, we would base our cotangent theta on an errored answer. So the better choice is this one, because we can be confident that we got the right answer for sine and cosine. You see where I'm going with it? Tan is the easier way to find the answer, but because we derive tan ourselves, in a testing situation, we might get that wrong. It's better to go with the data that you're given, that you have the most confidence in. I have 100% confidence in the data that's given to me in the question. My tan, I know we're good, but that one we had to figure out. So that one has more chance for error in it than what was given in the question. So it's better to go with the second option because we were given that data. Do you see what I mean, TJ, about why number 2 is actually we've got better luck that way, because this is dependent on if we got the right answer for tan theta. Okay. So that's why I'm going to do identity 2, even though you're absolutely right. This reciprocal identity would be much easier to figure out, but we actually have more trust in the second one, but they'll both give us the same answer. So I'm going to do cos of theta is 24 over 25 divided by the sine of theta, which is 7 over 25, which is the same as saying 24 over 25 multiplied by 25 over 7. Our 25s cancel out, so the cotangent of theta is going to be 24 over 7. And that's the answer to that one. So that one was a great question because we had to use identities to solve for like 4 different identities, just based, or 4 different functions based on the identities. But it was also a good example because there are more than one identity to solve each function, and so the question is, which identity do you choose? So thank you for that, TJ. That was a really good question to go over. That's it for those 3 questions. Are you okay with that third question? Are there anything that you want to ask me about this, or were you? It seems like you were following okay. Okay. So you have more questions for me. So I'm going to put up a new whiteboard, and then you can go ahead and paste your next question. Oh, there we go. When you're set. This is where I get a little antsy. I'm like, what? Because I have to think of, okay, what question is he going to put up there next? I wish I could say I use trig all the time. I find trig is really practical, actually, but unfortunately, I don't construct things often or in a boat doing location berries all the time, so I get rusty pretty fast in this stuff. So if I can't answer your question right away, TJ, I will definitely figure it out a little bit later, but I'll see what you got for me. Oh, it's up at the top. Okay. So use a reference angle to find the exact value of the following expression and do not use a calculator. So that I have to go back to my notes on reference angles. So the idea about reference angles is that, yes, section 5.4. So the first thing that you want to do is you want to just draw a unit circle. Dink, dink. There's my unit circle. And you want to approximate where 315 degrees is, and it's positive 315. So we know that we're looking at 90 degrees, 180, 270, and we're going to go a little bit over 270 to be around 315 degrees. So somewhere around there. That's going to be your 315 degrees from there. The reference angle, though, is going to be this point right here. That's going to be your reference angle, or theta prime. Are you okay with that part? Okay. The great thing about reference angles is that they're smaller angles and they're easier to find a trigonomic function for. So 315 degrees, that's a big angle and much harder to find your sine. But a reference angle is going to give you the same sine value. So what you're going to do is you're going to take 365 degrees is the full single rotation. You're going to subtract 315 degrees, and that's going to give you a much smaller reference angle to work with. So you can do that in your head. I never trust my head, so I always use a calculator, and that's going to give me my 50 degrees. So 365 subtract 315. Oh, what did I do? Oh, I have it in radians. Just a sec. That's not going to work. Take off my radians. Yep, that's it, 50 degrees. Oh, because why is it 365 degrees? Because one full rotation all the way to here is 365 degrees. And I just need to take my calculator off of radians. There we go, back to degrees. So 365 minus 315 gives me 50 degrees. Oh, no, it's 360. Oh, TJ. Now you're double guessing me. 180 plus 180 is 360 degrees. Where did I get the 365? Sorry, brain burp. I should stop while I'm ahead. I was doing so well too. Sorry. I'm glad you can laugh with me. 360 minus 315. So I'm looking at 45 degrees. Please don't trust me. 360. Yes, thank you. You're right. You haven't, yeah, that's good. Okay, so let's level set. One full rotation is 360 degrees, or 2 pi. We're good. We have an angle of 315. We're trying to find the reference angle. So we take 360 minus 315, and we're looking at 45 degrees. And we're all on the same page with that, TJ. So then what that's saying is that the sine of 315 degrees is going to give you the same numeric value as your reference angle of sine of 45 degrees. Are you okay with that? Because that's the gist of using reference angles, is that they're smaller angles, they're easier to use. So sine of 350 degrees is the same as sine of 45 degrees. And the sine of 45 degrees is a special angle, and you can look that up on your trig study sheet, and we see that the sine of 45 is equal to the square root of 2 over 2. Yes, so in section 5.2, we derive these special values from those standard triangles. And so you have to see how did we get the standard triangles? Look at the review video. They'll show you the standard triangles. And then from those standard triangles, they give you these ratios. And these ratios are more accurate than a decimal amount. But you don't have to memorize these special angles. They're on that trig sheet. So you can just go back to the trig sheet and you'll get used to knowing that angles of 30 degrees, angles of 45 degrees, and angles of 60 degrees, they give you those ratios on that trig sheet. And that's where I found this. And we'll always use reference angles. And that's why even when I gave that 50, when I thought that when I made the mistake that a full rotation is at 365, I was like, uh-oh, I think I'm off here because that's not a special angle. So here's that special angle. So sine of 45 degrees is equal to the square root of 2 over 2. But that's the numerical value of sine of 315 and sine of 45 degrees. The only thing you have to add on to that is what is the proper sign. Is it positive or is it negative? Now you might not be this far in the section, but basically it turns out to be this. We have quadrant 1, we have quadrant 2, we have quadrant 3, and we have quadrant 4. And on that study sheet, there's a little graphic, top right, that tells you what the sign is going to be for a specific function. And we see that in quadrant 4, cosines and secant functions are positive. That means all other functions are going to be negative. And you can see that our angle is in quadrant 4. So the only functions that are positive in quadrant 4 are cosine and secant. So that means that this angle, which is the reference angle for 45 degrees, has to be negative in that quadrant. So there are two things that you need to do when you are using reference angles to find exact values. You first need to change the big angle into your reference angle. And then once you get your reference angle, you have to physically observe where that angle rests in what quadrant, and then using the figure in that study sheet, it will tell you what the sign is. So you could get square root of 2 over 2 and have that as your answer, but if you didn't add the negative, you won't get full value for that question. So these questions are always sort of threefold. Draw your angle in the unit circle so you know what quadrant it lies. Find out what your reference angle is. That's going to give you your numerical value, and then figure out what your sign is going to be based on the quadrant that the angle lies. And that's given to you, I believe, is it 5.2 or 5.3? I think it's 5.3 that they talk about reference angles. Yeah, so in review video, section 5.3, they talk about what the signs of trig functions are based on the quadrant in which that angle exists, and reference angles are also in that review video for 5.3. TJ, do you want me to do another example of this. We can go through the fact of drawing it on the unit circle, finding the reference angle, and then finding the sign. Oh, okay. I'll get rid of this. Put a new one up. There we go. All yours. Okay. So this one's a little bit more difficult because we have tan in radians, but that's no big deal. What we have is the tan of negative 73 pi over 6. And they're saying find the exact value of this and using reference angles. The first thing we need to do always when we're finding the exact value using reference angles is we need to draw the angle in the unit circle. So if we were to draw the unit circle, I always like to take the radian amount and change it into rotations because I can visualize rotations much easier than radians. So I'm going to take, and negative just tells me what direction I need to go. So this is the positive direction, this is the negative direction, so I don't actually need to include my sign here. I could if I wanted to, but I'm going to take 73 pi over 6 radians, and I want to convert it to rotations. And I know that the conversion factor for rotations is 1 rotation is equal to 2 pi radians, because 1 full rotation gives me 2 pi radians. So one of the main things in trigonometry is being able to convert from degrees to radians to rotations and back and forth between them. And whenever I'm given an angle in radians, I am better able to visualize it through rotations. So I'm going to use this conversion factor of 1 rotation is over 2 pi radians, because 1 rotation is equal to 2 pi. So I'm just going to go ahead and multiply my numerators. So I get 73 pi over 6 times 2 pi, which is 12 pi. My pi's cancel out, and I get 73 over 12 rotations. Are you okay, TJ, in how I've converted from radians to rotations? Okay, so hopefully you've had some practice in doing those conversions and you're okay going from that, and this works out okay. Now 73 over 12, that can be hard to visualize. So what I'm going to do is I'm going to divide 73 by 12. So I'm just going to pop open my calculator here, and I'm going to take 73 divided by 12 gives me 6 rotations and a bit. So 6 times 12 is 72, so that means I have 6 rotations and 1/12 of a rotation left over. So 73 over 12 rotations is 6 full rotations of the unit circle and 1/12 left over, and it's in the negative direction. So what I'm going to do is I'm going to go around 6 times. So 1, 2, 3, 4, 5, 6. So 6 times, and then I'm going to do 1/12 of the rotation. And I know that if I'm doing rotations in 12ths, I'm dividing my unit circle into sections of 3. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so if I'm going to go around 6 times and 1/12, here is my actual angle, which is 6 and 1/12 rotation, which is also 73 pi over 6. So that's always the first step, is where is this angle actually on the unit circle? And I figured out that it was 6 rotations in the clockwise direction plus 1/12 of a rotation, which sets my angle right here. Now, what I need to do is I need to find my reference angle. TJ, are you okay in how I found where that angle was? Because I need to know that, because I need to know what quadrant it's in. And if this is quadrant 1, this is quadrant 2, this is quadrant 3, and this is quadrant 4, my angle lies in quadrant 4. So that was a lot of work just to find out where my angle is. So let me know, TJ, if you're following up to that point. Okay. So I know now it's all about finding this reference angle, this angle prime. And I know that that angle prime was 1/12 of a rotation. Now I need to know what it is in radians, because that's going to help me figure out whether I'm dealing what my reference angle is. So again, I'm going to use a conversion factor where I know one rotation, oh, and I don't have that going the right way. I know one rotation is equal to 2 pi. So I'm going to put my conversion factor as 2 pi over 1 rotation. That's going to cancel that out. I'll get 2 pi over 12 radians. And so my reference angle is going to be 2 pi over 12, but I can reduce that. 2 goes into 2 once, 2 goes into 12 6. So it's going to be pi over 6 radians. That is this reference angle here. So the 1/12 I knew because it was 6 full rotations and 1/12 of a rotation. I needed to figure out what this 1/12 of a rotation was in radians. So I used the conversion factor of 2 pi over 1 rotation. And I put rotations on the bottom in order to cancel out my rotations. And then this gave me my radians. I reduced 2 pi over 12 becomes pi over 6 radians. And that's my reference angle. So my reference angle, which is theta prime, is going to be pi over 6. TJ, how are you with that? That's the second thing. Find out where your angle is, and then figure out from that what your reference angle is. Okay. Now that I have my reference angle, pi over 6 is one of those special angles. Pi over 6 is 30 degrees. The original question, I have to go back up, is looking at tan. What is the value of tan of negative 73 pi over 6? That's going to be the tan of negative pi over 6. Whoops. And looking at my study sheet, the tan of pi over 6 is always equal to square root of 3 over 3. So now I have the value. the exact value of pi over 6 is square root of 3 over 3. And now I have to decide, is it going to be a positive or negative sign? And that depends on where the angle lies. Now, the angle lies in quadrant 4, and cosine and secant are positive. So that means all the other 4 identities are going to be negative. So my tan is also going to be negative. It's not based on this. Don't go by, okay, if my negative is here, then this is going to be negative. That's not what you go by. You always go by the location of the angle and what quadrant it is in, and then you're going to use the study sheet to tell you whether the function is positive or negative when it lies in that quadrant. So that graphic on my study sheet told me that the only positive functions in quadrant 4 are going to be cosine and secant. That leaves me with tangent, sine, cosecant, and cotangent as being negative for that quadrant. This type of question is complex because you're having to bring in the ideas of conversion from radians to rotations in order to draw the angle on the unit circle. Then you have to find your reference angle, which again takes a little bit of conversion, and then you're going to use your reference angle as your special angle, and then you have to figure out your sine. So it brings in all of section 5.2 and 5.3 together in order to answer these types of questions. And again, practice is big. So we've done 2 really good examples of here, which shows you the process, and then just practice these, and it will be easier for you when you do this later on. How does that sound, TJ? I know you've said you're going to go back and look at the review videos, which is great, and now you have 2 great examples too. So I think when you practice this, it will come together a little bit better for you for sure. Oh, for sure, TJ. Let me know. And then I can look over those for sure and get back to you with those solutions. That'd be great.